I don't know what the point in breaking up the last video was. Maybe it makes it more digestible. Let me know if it does or if it doesn't. Um, okay, so we were on the verge of defining a morphism of pre-sheaves, where if we started with a sheaf and we sheafified it, and then just simply forgot that we turned it into a sheaf, so that we could compare these two things, right? And in particular, we had hoped that this map, let's just construct a map and not get ahead of ourselves, but it should be the case that F, if it was a sheaf to begin with, that we should get an isomorphism. And well, maybe this particular map witnesses that isomorphism. And maybe this particular map is even defines a natural transformation from the identity on the category of pre-sheaves to this composition of sheafification and the forgetful thing. So what do we have to do? Well, we need to supply a way of going from sections of F over U to sections of the forgetful functor of the sheafification of F over U. So in particular, I need to produce some function from U to the product over all the stalks. Well, suppose I had some S that was in here. What am I going to send it to? Well, again, this is a function defined on U, so it's enough for me to tell you where it sends each point X. And each point X needs to land, when I evaluate this at X, specifically it had better land in the stalk at X. But S is a section over U, so I can just define this to be the germ of S at X, right? So certainly I've defined a function here. And then let me scroll up because I have the condition written up here somewhere, right? I need to convince you that for all points in U, I can find some open set such that, and some section over said open set such that the stalk, the germ of that section is equal to the value of this function. Well, that's pretty trivial to do in this case, right? Because S already, I could just take for that V above, I could just take it to be U, right? And we already have this condition, right? My function is equal to S at X for all X in U, which is the V here, right? So this definitely does land in here. And again, you'll want to check, right, if, for sheaves of abelian groups or vector spaces, whatever, that you'll want to check that this actually defines a map in that for those algebraic objects, okay? Great. So now we have some way of comparing these. And let's suppose now, so suppose F is a sheaf. Well, then I claim that theta is an isomorphism. And we're going to use this result. If you're upset as to why I didn't explain this proposition from Hartshorne is true last time, which says, it's enough to check the induced map on all the stalks. Well, I think the proof there is pretty clear. Again, maybe if you ask me nicely in the comments, I can walk through it in a future video. Okay. suppose F is a sheaf. We want this thing to be an isomorphism. So well, what did I use? Did I write, what did I make in my notes here? I want to be consistent with my notes because I'm going to get myself confused. So let X be a point in our space and consider the induced map on the stalks. So theta sub X for of F plus X. And okay, so the first thing we're going to do is check that this is injective, because that's, in my opinion, the easier one. So we need to choose some representative of germs, equivalence class of some representative of a germ. So let's let U be an open set containing X, and S be some section over U. Okay. Such that we get the zero. I'm going to call this, I don't know, X plus. So by that, I mean the zero element in the stalk of the forget applied to F plus. So that had better be what we get when we apply theta sub X to this equivalence class. And remember that this equivalence class is just, by definition, we take the same open set and we apply theta sub U to S, right? So what does that mean? Well, I mean this, so I claim in general, I don't think we've talked about this, but, we have to guess for a sheaves of abelian groups, they need to have an identity element. So what is going to be the identity element of the stalk? Well, I claim it's just the constant function. So this will be U, and this will be the zero function, say zero sub U to be the zero element of F over U, right? Well, so I suppose here I should say 4 of F plus of U, right? So what does it mean for these two things to be equal? Well, it means that there exists a open subset in the intersection of the two open sets. So in other words, that just means that there exists some open set specifically between X and U, such that the zero element restricted to the subset is the same as this function restricted to the subset. But what does that mean? Well, this is just the zero element in V. And what does that say? Well, if these things are equal, then that means if I apply this to any element y in V, so that's theta sub U of S, that's just evaluation at X. Well, that's gonna just end up being 0, right? So 0 at that particular what have I done here? Oh, this should be a Y. Sorry, there should be a Y, right? And so what does that say? That says, I mean, remember, by definition, this was supposed to just return the germ of S at Y. So what does that mean? In other words, right, we know that for all Y in V, the germ is 0, right? But that is exactly, so in other words, that means that V S restricted to V, that means that this is the zero element of the stalk of F at X. But this is the same thing, right? Because this is the same thing as, right? I claim that these two germs are equal, right? Because of course, all I've done is I just took this function and I restricted it to V. So that implies that the germ we started with must be zero, hence the induced map is injective. Okay, so I know that's a little confusing, but this is like a very instructive proof about how things normally go with sheaves. We just, sort of can like check things on these local levels on stalks and germs and whatnot. Okay, so the other thing we need to do is prove that this is surjective. And I swear someone can come up with a better proof than I did. I just decided to take the most direct kind of right down to the definitions version. There's maybe a more slick way to write this. But okay. So what are we gonna do to prove that it's surjective? Well, let's suppose now that I had some S that was in the open set of the sections over the open set here, right? So in particular, I've got some function, the usual thing, such that blah, 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 some properties, which I'm going to call upon in a moment. And now we need to try and come up with some, yeah, I think somewhere I think I missed out on I forgot to declare as using the property that F is a sheaf. And yes, so that's exactly this implication, rather that S restricted to V is the zero section, right? So that actually uses one of the two extra conditions that we put on a sheaf instead of a pre-sheaf. So yeah, important to point that out. And so we're also going to use the other condition here to prove the surjectivity. So that says basically, if we have a bunch of locally defined sections, we can glue them up to a globally defined one. So the general idea here is in order to construct something that maps to rather, what am I saying here? Rather, I'm trying to suppose I have some US in the stock of this thing at X. Sorry. So in particular, that means U is an open set containing X, and of course, S is this function here, plus some special properties. And so we're going to use the sheaf condition, right? We need to try and construct some element of S F sub X, which theta X will map to this germ here, right? Okay. How are we going to do that? Well, oh, didn't mean to pause screen sharing. I actually lied to you. I'm not going to use the second property here. We use it in the so-called universal property. But I digress. Okay, so we've got a germ, right? Got a germ. And we need to construct something that's going to map to it. Well, by definition, or since um, uh, since S is in particular, right? S is in here, right? So it's a function here with some such special properties. Well, that property says that in particular, we can choose an open set sandwiched in between X and U, and we can find a T, which is a section of F, such that for all y in V, the germ of T at y is just the value of the function S at y. Well, if V is sandwiched between, if V is an open set containing X, then that means that the equivalence class, where I have V and T is in V, so I'm allowed to put it in the second place here. Well, this is in the stock of X at X, right? And if I apply my localized map to this germ, well, what is it? By definition, this is V theta V of T, right? But now theta V of T is a function, and in particular, if I evaluate that function at some y, well, by definition, right, the definition that we took of theta V, that is just going to be the germ of T at y. But because y is an element, so for y in V, because y is an element of V, we know that that's just S of y. In other words, right? In other words, T, the theta V of T, is equal to S. In particular, that means that these germs, rather the theta X applied to this, is equal to well, V S restricted to V, but that is, remember, the same thing as US. Okay, great. So that actually concludes the proof that if F is sheaf, then theta is an isomorphism. Okay. Well, that settles that. Okay, but there's a little bit more to say. So in particular, this satisfies an example of something called a universal property, which I think we've discussed before. But what this says is there's one more piece to this puzzle. So not only do we have now this special map, comparing what happens if we sheafify our pre-sheaf, that also realizes an isomorphism between our pre-sheaf and our sheafified thing if the original thing was a sheaf. But also it's even a little bit more general than that. So which is going to be wrapped up really nicely, sort of put together in a nice way in the next video. But it says that for all sheaves, G, and for all, let's say, maps from F to forgetting of G. So remember, G is a sheaf, F is a pre-sheaf. Strictly speaking, to compare them, I should forget G's sheaf-like nature. For all such maps like this, there exists, so let me write it this way. So this is our map theta from before. There exists a unique map, F tilde, that makes this diagram commute, right? In other words, there exists a unique map where doing F is the same thing as applying F tilde to theta. So this map is extra special. Not only does it compare all of these sheaves, but it says like, yeah, if you had any way of comparing F to any sheaf whatsoever, it specially it's got to sort of factor through this map theta uniquely. Okay. So the name of the game here is going to be to construct the map F tilde. And I guess I'm going to leave the uniqueness of the map F tilde to you. It kind of comes out of the construction that we're gonna do, right? So what do we need to do? We're trying to define a map of sheaves. So that means that for some open set, I need to supply you with what this map F tilde is going to do on the open sets. Uh-huh. And probably its construction should somehow involve F, right? Because it's going to have this special relationship with F. Okay, so how do we define such a thing? Well, let, S be, well, I should say let S be in here. So that translates to let S be some function here, such that blah, 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 the special defining properties. And I'm going to have to somehow construct a way to map this into this other sheaf G. Well, this blah, blah, blah defining property, remember, I do already F already gives me the datum of a bunch of maps here, right? And somehow on the small scale, these functions look like stuff in here, or rather subsets. So maybe I can lean on that local feature and glue things together. This is the idea of how things work with sheaves, right? So because of our defining feature, for each x in U, we can choose some Vx. I'm going to label it sandwiched in between X and U. And I'm going to call this thing, so people probably hate me for cumbersome notation, but I want to try and keep track of all this data. Some section of F over V sub X. And so I have the subscripts because of the dependence on S and the dependence on X. Right. Now, these are things that I could apply F to, right? So consider, if we applied F at V of X to TSX, then this is going to be a section of G over V of X, right? So I can define a bunch of these sort of small local images, and note that the set of all v sub x with x and u is a cover, of u, right? So if I could show that all of these things, that each of these images agree on all of the restrictions to the intersections, then I know that I can glue it together to some global element of G over U, right? So given some, x and y in U, and let's say, well, z in the intersection of these two, consider, well, I'm trying to show, well, in particular, so f vx t s x tsx. I want to take this thing, I want to restrict it to this intersection. And the way that I'm going to go about this is if I can show, remember now G is a sheaf, right? We've taken these images, so we're living in a sheaf now. And if I can show that the germs of each of these sections all agree for every Z in the intersection, then the sections themselves have to agree, where I'm leaning on the sheafy nature of G in order to make that true. Okay, fantastic. So what I can do is this the way that I wanted to prove the result? Oy, oy vey. Oy vey. Well, there's also the matter of making sure this is well defined, but in any case, the restriction of this, well, that's going to be f of v intersect yv applied to t sx restricted to the intersection. Because remember, f is assumed to be a sheaf morphism, so it respects the restriction maps. So we can look at this thing in particular. So T S X restricted to Vx Vy. Well, the germ of this thing is just going to be the same thing at Z, is just going to be the same as the germ of this thing at Z. And the germ of this thing at Z, well, we know that is going to be, because these, we know that is going to be equal to S Z, particularly because Z lives in Vx. But it also lives in Vy, so we know that that's the same as TS Y. That's germ at Z, and by this sort of reversing this argument, that's the same thing as this. Right. So the germs of this thing and this thing are equal at everywhere in the intersection. And because G is a sheaf, it means that these two things are straight up equal on the intersection. And so, of course, then applying the same map, right? If this thing on the left is equal to this thing on the right, then that means, of course, that if I just apply the same map, I have to get the same thing. So this is TSY restricted to VX intersect VY. And then that is V f at vy, t s y restricted to vx intersect vy. So what that means is, so therefore, because G is a sheaf, right? And I've shown, right, these VXs cover all of U, and the restrictions of each of these things to the intersections all agree. Therefore, there exists a unique element, T, I'll call it TS, which lives in GU such that TS restricted to each of the VXs is equal to TSX. Yeah. Or sorry, is equal to F of TSX. Yeah. So sorry for all the confusing notation, but therefore, so now finally we define F tilde of the S we started with to be T superscript S. Okay. So the last thing we need to do then, so again, actually I've just told you how to define this. Remember, we're trying to prove that this is a sheaf morphism, so you should go through and check that this is compatible with all the restriction maps. Moreover, there's technically a well-definedness result that we need to check here, right? Because like a priori, you could have, right, we're using the property, the defining property here, you know, that there exists some choices of Vx and TSX in f of Vx, right? But what if we made different choices of those? Well, because of the sheafy nature of the whole situation, this map is still going to be well defined, basically because of this restriction property. So, but there are things to check there, and I am not checking them. But I want to be clear that, you know, there is technically more work that needs to be done. Okay, so finally, how are we going to go about? Let me check my notes. Proving that these things are, in fact, that this factors through. We just need to prove now that the composition of these morphisms is equal. So suppose that we had some A over U, right? Well, then I want to know what F tilde U of theta U of A is. And remember that these Vx, they cover U and G is a sheaf, so it's going to be enough to check those restrictions. By definition, this is just this section T that we built out of theta U A. In particular, the one right, restricted to Vx. Yeah, so this is this part here, right? By construction. This was just the labeling we gave for that. Okay, fantastic. But now remember, so given y in Vx, note that the stalk of this thing, of course, is just the same as the stalk of this thing. And the stalk of this by construction, well, that's the same as the stalk of T, X, Y, the stalk of this thing. And by construction, the stalk of this thing, we said, had to be equal to the value of this function at Y, right? Um, and okay. But we know that by construction, the restriction of this thing is exactly f of at Vx of t theta u a comma x, right? Okay. But remember that we're starting with some a that is in f of u. So in particular, when we're choosing these, so note that a restricted to Vx, if you took its stock at any y, that's just the germ at y, that's just the germ of a at y, and that is theta u a evaluated at y. So in other words, this satisfies the defining condition of f plus u. So in particular, when we chose these t with the superscripts, I could have chosen this to be that representative. And now, okay, there's the little part that I formally didn't verify all the details, that it doesn't depend on those choices. But if you did that exercise yourself, or choose to believe me, that means then that this whole thing is f sub Vx of a restricted to Vx, but that is exactly f of u applied to a restricted to Vx. And finally, once again, now I have this is equal to this, and the Vx cover u, and G is a sheaf, and so it had to be the case that actually these two things were straight up equal. Okay, so that gives the result. What a long and crazy video. So I will highlight again. Remember that what we just proved is this thing called a universal property. And remember this vibe of mapping what is essentially, even though I haven't described, what this thing is supposed to do, prescribed morphisms coming with it to really give you a natural transformation. We'll come to this in a later video, but we've more or less done this thing where we defined a natural transformation from an identity functor to a composition of functors. And in the next video, we're going to get into some real abstract nonsense about that. So that's all for today. I'll see you again soon.